So I made these problems sound like they were going to be all real life, and I will do one more problem that's very realistic. But this one, maybe not, who knows? But we're just asked to find two positive numbers whose product is 144 and whose sum is minimal. And I wanted to do this one with you, even though it's not necessarily directly applied. It could be. You could imagine a situation when it was. But this problem is a little easier to get our minds around, and it'll help us with the next problem. So this is going to introduce some techniques that we'll need. So just a couple of things. First off, you are given no labels. So you need to come up with some names for things. You've got these two numbers. We should name those. So use variables and then write down everything you can. So the way that I would start this is I would say, look, let's let x and y be positive. These are positive numbers. And then we want to assume that their product is 144. Okay? So then we should go ahead and say what we want to optimize. So we can't write today. So we want to minimize S equals x plus y. And so right away, we've run into something we haven't seen before, and where the thing that you want to optimize, in this case minimize, actually involves two variables. Notice there's x and y. This is Calc 1. This is a one-variable calculus course. So what do? Well, you can solve for one of the variables in this equation and then plug it into that equation. By the way, this equation is often called a constraint equation, and the equation that you want to minimize or maximize, whatever the case may be, is often called your objective equation. So you somehow plug your constraint into your objective equation. And so let's see how to do that. It doesn't matter which variable you solve for in general. Pick one that's easy and convenient for you. In our case, it's identical, but in the next problem we'll look at, there is an easier variable. So sometimes it matters, and you might save yourself some work. So we just know that xy equals 144, so then I'll just solve for y. Y is 144 over x. And so now I know that s, which, by the way, I'm going to think of as a function of x now, is going to be x plus 144 over x. And that's what I want to minimize that. When you want to minimize something or maximize something, you maybe in your mind you wonder, does the extreme value theorem apply? And by the way, the extreme value theorem applying, all that does is guarantee you that there's an absolute max or min. And it tells you that you just need to check the local extremas and the endpoints. In my case, it doesn't apply. There are no endpoints. Here, I just want two numbers who are positive. So my interval is 0 to infinity. It's not a closed bounded interval. So I'm actually not guaranteed a solution to this problem. That makes it kind of fun. It's intense. But I'm still going to go ahead and proceed using tools from calculus, and we should be able to verify our answer. So I compute the first derivative. I get 1 minus 144 over x squared. I want to know, where is this guy equal to 0 or undefined? Well, it's undefined when x is 0. So we'll go ahead and mention that. So my critical points are going to be x equals 0 for starters, because it's undefined right there. Let's solve it equal to 0. So I get 1 equals 144 over x squared. So x squared is 144. I get x is plus or minus 12. Both of those are critical points. However, we're only interested in x values and y values that are larger than 0. So we'll go ahead and say, but x bigger than 0, so we only care about x equals 12. So the critical points are x equals 0, x equals 12. Actually, I can even ignore this x equals 0 because I want x bigger than 0. I want x bigger than 0, so I'm not interested in x equals 0 either. I just wanted to mention that technically it's also a critical point. I'm going to make my number line for s prime. I'm going to put my restriction. I'm forced to be bigger than 0, so I do want to make sure that 0 goes on there, not because it was a critical point, but because everything has to be bigger than 0. So get that on there. Then you've got your 12. And now you want to fill in your number line. So I encourage you to do this yourself. Plug in something bigger than 12 into S prime, and you're going to get out a positive. Plug in something between 0 and 12 into S prime, you're going to get out a negative. And so now you can see that, yeah, there's a local minimum there. May not be an absolute minimum, except that you know that it is, because from 12 on forever, your function is actually increasing. So you're decreasing from 0 down, and then you are increasing forever. You don't need a full graph of this function. You can see that actually that's an absolute min. So let's write this up now as best we can. So we can say, so thus, S of x has an absolute min at x equals 12. And what does that actually mean for our problem? We wanted two positive numbers whose sum was as small as possible, whose product is 144. So we've got one of them, we need to find the other. We should say i.e. x equals 12 and y equals 12 have minimal sum. Let's say have product 144 and minimal sum. And again, the takeaway here is that the extreme value theorem didn't guarantee us an absolute min, but we were able to figure it out that it does have one, and we were able to use calculus just to think about it and realize, look, if you're increasing from 12 on, then there's not going to be another minimum somewhere else. So that's it. All right, so we'll do one more problem, and then we're good to go.